Hi, today we're going to be basically continuing right down the pathway of significant figures, so I'm just going to get into it. If you would like a bit of a refresher from the last lesson, go ahead and hit the pause button, try and answer these four Regents questions. Otherwise, I'm just going to kind of walk into them myself. I can see here that there are numbers every 10 degrees, and then there's these slightly smaller lines, so that's like halfway every 5. And then there's 4 individual lines, so each line is 1 degree Celsius, which means when we make our reading, we have to go to the 10th of a degree Celsius. So it looks like it's between 4 and 5. I would guess it's about 4.5, maybe a little less. Looking at our answer choices, only one makes sense, between 4 and 5, and goes to the 10th place. When it comes to significant figure multiple choice Regents questions, you really only see questions like this. The free response section, you might get some more like, how many significant figures does this contain? But it's really this. So going through the dot left, not right, nope, that's backwards. Dot right, not left method. Really quickly, this would be 4, 3, 3, and 2 significant figures. We're looking for the 4. This is 1, 2, 1, and 3. We're looking for the 3. And this is 3, 2, 1, and 2. Again, we're looking for the 3. So I'm actually going to go backwards from our usual method, and I'm going to start with the application and then double back to the thing we have to talk about, because we kind of talked about measurement and significant figures, and we can apply that here. Sometimes when measuring the volume of an object, if it turns out to be a regular object, meaning all of its faces are polygons, you can just do some geometry, length times width times height, or pi r squared h. But when you have something irregular like this lightning bolt, which appears to be three-dimensional, I don't know what kinds of polygons it's made up of, and yes, I could figure it out. And instead, what we would do is we would do something called water displacement. Add substance to water and measure delta V, change in V, right? This means change. And when you're looking at change, usually change means final minus initial. And so here, delta V is going to be equal to Vf minus Vi, or V2 minus V1. It's always the second measurement minus the first measurement. So coming over here, we've got Vi or V1, and then we've got Vf or V2. The Vi here, I'm looking, there's lines every 2, which is super not helpful, but it does happen sometimes. It looks like it's pretty much on the line. So actually, I'm going to say it's 46, but I'm estimating that next digit to be a 0. It's probably milliliters because it's water. But yeah, it's okay. You are obligated to add a 0 if the instrument isn't really telling you anything and you think it's exactly on the line. Your estimated next digit is definitely cool to be 0. And then this one up here looks like it's just shy of 54. It looks like 53.9. So milliliters. So that would be 53.9 milliliters minus 46. And that would be equal to almost 12. And we go from there. But if you want to calculate density, there's a link to your reference table right above my head. Well, above the gold that's above my head, if you need it. But the formula is on the back cover, m over v. The problem gives us a mass, so we can plug that in right away, but we don't have a volume from the actual problem. The volume is V here equals Vf minus Vi, which is equal to, oh, I don't know, I think that's about 19.8. I see lines, big lines every 5, and there's 4 between them, so each line is 1 milliliter minus 17.2, which comes out to be 2.6 milliliters after we do our subtraction. That means that number gets to go right up there. And we can divide, and we get 19.9392308 grams per milliliter. There's a question that you want to be asking me, and you want to be saying, Mr. Mulick, where should I round? Because I don't want to write down all those numbers. And the good news is, in chemistry, you don't have to. Before we get into how to round, I have one more last extension of this that the reference table likes to ask. It turns out that since the object that we were measuring the density of was gold, we can go to table S and it's an element, obviously, and there's properties of selected elements, and one of the properties is density. So this is gold, it's number 79 on the list, so I cut out a bit there, but you actually get a reference value for the density of 19.3. We didn't get 19.3, which means we can calculate the percent error in our measurement. The formula for percent error is given there. That is going to be our measured value from the previous slide, which was 19.9392308 grams per milliliter. I was about to write down the other number, and then I realized that the units don't match. In fact, I'm going to erase this so we can see. You can see the units for density given are grams per cubic centimeter, and the density that we calculated was grams per milliliter. So it's probably worth mentioning that 1 milliliter is the same amount of volume as 1 cubic centimeter by definition. So you can picture kind of like a centimeter, and a centimeter is a little cube. That is a milliliter of space. So luckily we can just convert that easily, and our accepted value is 19.3 grams per milliliter. We're going to divide all of that by 19.3 grams per milliliter times 100%. You do need that step in there. And then when you do your math and your subtraction, you get 3.3121%. And so the question again comes up. I don't really like having all of these numbers there. So is there a reasonable place that I should be rounding when I do math and chemistry? And the short answer is absolutely. And then there's a longer answer behind that. So math deals with exact answers. You put in 1 divided by 7 to your calculator, you get this big long decimal, and it just keeps going. That's not how chemistry works, because you'd never really say 1 divided by 7, because those numbers are just the magnitude of a measurement, and measurements coming from instruments are finite. That was all what we did in our last lesson. So the rule that we're going to follow for this course, for chemistry, for science as a whole, you need to round after you do math so that your number, your measurement, does not convey too much or too little information. So back to the box that I had, I copied the box over, so it's exactly the same size. I copied 2 of the rulers. We're going to use the middle ruler so that it makes our calculations interesting but not too interesting. So if we remember from our previous lesson, this is 8.2 mud, and if we're going to estimate our height on this one, I'm going to estimate, this is your width, nope, that's your length, your width, we're going to say that's 1.3 mud. So we can write this out, and we can calculate that as 19 mud. And then for the area is length times width, 10.66 mud. And so if we go by our rule that math cannot make our number better or worse in terms of precision, which precision is the word for the number of significant figures in your data. The more precise, the more significant figures. Accuracy was the percent error that we did before. So if we say that, each of our measurements goes to the 10th place. So it would stand to reason that when we do math, that was our uncertain digit. And in fact, you should make sure that that is still the uncertain digit over here. So I'm going to say that it's not 19, but 19.0. This was an interesting case insofar as you actually ended up adding a decimal place instead of removing one. Typically what happens is you have to round your answer back, but sometimes you see you have to add a decimal place. To show an example of the opposite, if you had 1.2 and you were adding to it 1.45 grams, just adding up some masses, remember that this is a complete question mark because this 2, because it's a measurement, is uncertain. This 5 is uncertain. But the 2 is uncertain, so I'm not sure that 2 plus 4 is 6, sure, but then the next digit in that measurement, we didn't know. The machine didn't give it to us. The instrument did not tell us this. So you can't say, I don't know plus 5, because you don't know what I don't know plus 5 is. Is it 5? Is it 6? Is it 13? I don't know. So you can't do anything with that. That's why we end up rounding our answers to line up with the numbers that go in. So the rule is that you have to say this goes to the tenths, this is also the tenths, and so on. So your answer has to go to the tenths place. When you multiply and divide, frequently powers of 10 change after the multiplication or division, so it doesn't make as much sense to round to a decimal place. We instead round to preserve the precision, so we look at the number of significant figures. So if this is a 2 significant figure measurement and this is a 2 significant figure measurement, you can probably guess that our answer should have 2 significant figures. But 10.66, that's a 4 significant digit number. So now we have to round such that our answer would have 2 significant digits. The actual, based on this ruler, these rulers, the perimeter is 19.0 mud and the area is 11 square mud. If you would use the less precise ruler, maybe the answer would have been 20 mud and 10. And if you use more precise, then maybe you would have added a decimal point somewhere. So in general, we can go back to the problems that we saw before, and we can now answer that question more correctly. The density for this gold is equal to 51.842 grams, divided by, we said, 2.6 milliliters. And so again, we want to write our answer of 9.939238 grams per milliliter. So then the question becomes, how do I round this? Well, this is a 5 significant figure number, and this is a 2 significant figure number. And since this is division, we're going to go with that second rule I mentioned. And our answer needs to have 2 significant digits, which means we're going to round to that decimal place. Since the answer is 19.9, though, that said, 20 contains 1 significant digit. And so what we'll actually end up seeing is something that we saw previously in looking at a couple of problems where there's this mystery dot, right? We know that already. That means 2 significant digits. So we're good. If we wanted, for some reason, this is where another way to do this, we could write this in scientific notation. You might be asking why we would do that here. There's not really much of a purpose, but in scientific notation, all of the digits end up being significant because there's always a decimal point. So this is a good way to say if you had a measurement like 200 and you wanted to say this is significant and this isn't, you would rewrite that as 2.0 times 10 to the second grams. If you wanted 1 significant figure, you could write it as 2 times 10 to the second, or 3 would be 2.00 times 10 to the second. You don't have to use scientific notation, but sometimes it ends up being the only way you can really do it. So to summarize, there are formulas in the reference table for density and percent error. When you're adding and subtracting, we'll stop at largest final decimal. Whichever is your worst, furthest left, biggest final decimal, that's going to dictate how you need to round your answer. And when you're doing multiplication or division, the answer contains number of significant figures that is same as the least precise. In general, this process improves with practice. So if it's not super clear yet, I imagine it will be shortly. Thanks for watching.